Okay, I think we're on the air.
Yeah, I just got to press this thing here. Okay, I think it's working now. Oh, so I start now. Is that right? Okay, so so I'm trying to remember what my homework assignments were. Some we said out loud, and some maybe I assigned to myself later on or something like that. And so one of them I just flat out didn't do. It's very important, but it's not on the schedule for today. It's, you asked some questions about the Kleinian geometry aspect of the designs last time. I guess, there was this idea of the regularization of a design, which is like switching to the torser picture from the geometric figures picture. And you were asking some good questions about that, and it's really important. So it's definitely on the schedule, but not for today. Let's see. So what's the other homework assignment? The other homework assignment is well, first of all, we had this issue of how to use these Zoom whiteboards. Can you turn on a Zoom whiteboard or something so we just practice for a second? I guess we should have practiced that before we started, but it's relevant. I mean, I want to do something with it right now. I mean, it's the same reason that we wanted to use it last time. Okay, I should try to turn it on. Well, let me tell you why I would like to use it. So I was drawing some designs last time, allegedly a pair of designs. Let me go back to the page here that has this. It should be right over here. Yeah, and right, again, maybe we have a slightly different picture of this. Maybe we don't have a slightly different picture. Let's see. So that's the picture, and I think you were telling me at the end of last time, what I remember you telling me, and we were kind of short on time, but I thought you said something like that these two designs have equivalent period lattices or something like that. And that's the reason I thought it would be good to have the Zoom whiteboard that we could both draw on right now, to argue that out, because I'm still not quite seeing. I have an argument that says that they're not. I mean, I'm not completely sure I understood what you were asserting, but you were telling me, we were looking at this picture. Does this make any sense? Do you remember what
Yeah,
the
it makes sense. Yeah, it makes sense. I'm just busy trying to see how I could be wrong.
I mean, if you want me to try to if you want me to try to give you my argument about why these two parallelograms can't be fundamental domains for the same elliptic curve, I could try to give you my argument for that.
Yeah, why don't you try to do that?
Okay.
And I think it's better to just do it on the screen you've got. Yeah. Okay.
Okay. So the fundamental domain, well, right. You can take the fundamental domain for an elliptic curve to be a parallelogram.
Yep.
But if you include reflections, then it's actually, you can cut that in half. So it's like a triangle. And I always find that convenient in a lot of ways. I kind of stumbled upon this myself, but I forget who else has emphasized this. That there's a nice sort of normalization thing here. That it's with a few minor glitches. There's like a unique acute triangle. So all you have to do is I'm claiming that all we have to do is make sure that the acute triangles here, and right triangles count as honorary acute triangles. That's one of the minor little glitches here. So we just have to find the acute triangles for the the acute triangles that are halves of these parallelograms, and check that they're not the same acute triangle, basically. And it looks to me like one of them has a right acute triangle,
right,
and the other one has an isosceles acute triangle.
Yeah, but then you have to convince me that there's a unique acute triangle.
Okay, okay. So, okay, now I'm going to switch back to today's page here. So, am I doing this right? So I think the best way to convince you of that is to just fool around a little bit with the moduli stack of elliptic curves. I can't remember any of the names of any of the drawings that people draw here. It's like a picture of the upper half plane with, well, you can tell me names for what I'm trying to draw here. You can probably draw them better, but let's see. I want to draw like an upper half plane, so I'm drawing the boundary of the upper half plane. And maybe that's the origin there. Well, actually, I think the first thing I want to do is I want to draw the moduli stack. Right. Okay, never mind the moduli stack elliptic curves. Let me just draw the moduli stack of acute triangles. In a way, that's a lot easier to understand. So the moduli stack of acute triangles goes like this. So your acute triangle is going to have a side. So let's draw one of the sides of your acute triangle. Okay.
Okay.
And now we're trying to figure out where we can put the third corner of the triangle. Maybe I'll erase this other thing here over here. Okay. So think about all the places we can put the third corner of the triangle and have it still be acute. And
are you only doing it in the upper half plane here, not in the bottom?
I guess so. I guess I already decided that the exterior of the triangle is downwards, and I'm being very sloppy here. I don't know why I decided that, but yeah, the interior of the triangle is going to be in the upwards direction. So, so one constraint is for this angle on the left to be acute, you better not violate that perimeter or whatever.
Yep.
And you better not violate this one, or else the right, the angle on the right will go non-acute. And you'd better not. So where is it here? Damn, I drew it at a really awkward place, right? There's 7 of those. Is that right? 1, 2, 3, 4, 5, 6. So it's 3.5. So there's like a semicircle here. And it's a famous Euclidean geometry thing here that's where the right, that's really bad drawing of semicircle. But right, that's a famous Euclidean geometry little exercise or something. It's kind of fun.
Yep. Yep.
Seeing why that's where the right angles are. So those are the, so our moduli stack of acute triangles is starting to be like this. This is sort of like the moduli stack of acute triangles that have all their corners named, like red, blue, and green or something like that. But we probably want to, mod out by some symmetry. We probably don't want to have the corners distinguished from each other or something like that. So like, where's the, I mean, you can also, right, just conformally or something. This is really just an equilateral triangle. It doesn't look very equilateral. Right, there's something mystical about the fact that the moduli stack of acute triangles, if you squint at it in the right way, maybe conformally or something like that, it itself looks like an acute triangle. The idea of having a moduli stack that looks like the same kind of thing you're classifying, vaguely, if you squint hard, is sort of suggestive of various things. I don't know what it's suggestive of exactly, but yeah. But there's just kind of the symmetry of the 3 bang acting on the equilateral triangle. If you want to have the moduli stack of oriented triangles, then you only mod out by the rotations, et cetera, et cetera, et cetera. But I hope you're getting the point that you could probably explain it to me much better than I can, that this picture that I've drawn of the moduli stack of acute triangles should already remind you of the moduli stack of elliptic curves. And when you clarify that, when you think that through, it turns into that assertion that I made, that you have to say it the right way. I hope I said it close to the correct way, but and the glitches have to do with the way that right triangles are honorary acute triangles. Let's see. Oh, right. So if you if you what is this line? This line has something to do with something, right? What is it? That midline.
Yeah.
Right. That has to do with right. If like I said, that folding thing has to do with if you want to, not include the orientation as part of the structure. And then this is convenient, sort of, because now you see that we've got part of the boundary is right triangles. I guess this other part of the boundary is also right triangles, but this part of the boundary, the midline, now becomes the isosceles. So they're sort of on the extreme frontier from this point of view.
Yeah.
So there's this interesting sort of duality, or duality isn't quite the right word. There's an interesting dual role played by the right acute triangles. Again, maybe some people don't consider right triangles to be acute triangles, but they are honorary acute triangles. They're just very close to acute. And the isosceles acute triangles, those are the two extremes that correspond to the real elliptic curves. Because of this extra symmetry that they have, this extra orientation changing symmetry that they have, right? An isosceles triangle has this orientation exchanging symmetry, and that makes such an elliptic curve into a real elliptic curve. And right triangles also have that orientation exchanging symmetry, but they do it by is that right? What do I mean?
Yeah, I don't know.
Yeah, the parallelogram. What do I mean by that? It's true in some sense that the elliptic curve that you get from a right triangle has an orientation exchanging symmetry.
Yeah, I mean, it has two right.
That's right.
A rectangle has two right triangles in it that are orientation reverses of each other.
I think that's right. And so there are all those real elliptic curves that have no real points. They're sort of, all the points are sort of completely imaginary or non-real, at least. And those are Klein bottles. When you fold by the orientation exchanging thing, you just get Klein bottles. But the more fun ones are the ones that actually have points. So they actually have a base point. So you can actually think of it as an abelian group object. And those are either Möbius strips or what? Möbius strips or non-Möbius strips, I guess. So there's two kinds of elliptic curves, and one of them comes from the two kinds of real elliptic curves. Two kinds of real elliptic curves that are not completely invisible. And one of them corresponds to the isosceles triangles. One of them corresponds to the right acute triangles. And yeah, I'm giving you a lot of extraneous information. I'm giving you a lot of extraneous information here, but it's
What do you mean by saying a real elliptic curve could be a Möbius strip or an annulus? So those are two-dimensional surfaces with boundary.
Yeah, I actually showed you this movie one time, the dripping faucet movie, where it starts, the moduli stack is just one-dimensional. It's like a movie, and it starts out with the droplet about to form, and so that's actually a Möbius strip. But eventually,
how can a real elliptic curve be a Möbius strip? A real elliptic curve should be a one-dimensional real thing.
No, but it has, it's,
But do you think of it?
you're probably mistakenly thinking of a complex elliptic curve as having something more than a real elliptic curve, but it's sort of the other way around. I mean, a real elliptic curve is a complex elliptic curve with a way of folding it. So the boundary, you know, it's like a right. A real elliptic curve is right. It's really like a manifold with boundary, but the boundary is the real part. You know, the non-real part is the thing that
so
is
you're
bounded.
thinking of it as a complex elliptic curve with a anti-holomorphic involution.
Exactly, which may fix some points.
I was thinking about the fixed points, but you're thinking about the quotient.
That's right. So there's a duality there between the co-fixed points and the fixed points. Yes. And right, you can see this droplet that begins to form and it breaks off, and that's where it switches from being, you know, the isosceles triangle. Am I saying this right? I think it's the isosceles. Yeah, the isosceles triangles that give you the single component, the Möbius strip. The boundary has a single component, and it's the right triangles, I think, that give you the normal non-Möbius strips, where the boundary has two separate components. But all of this is, just fun.
Mainly you're proving it by the method of like convincing someone that you know more about this stuff than they do, so that you're probably right.
No, I'm just saying that you just have to check this picture here, this picture over here, this one that I'm hovering the cursor thing on. You know, that you should recognize that as a little component.
Yeah, I certainly recognize that picture. Yeah.
And I'm just saying, just stare at that picture and think about it. And what it's saying is that, you know, if you say it the right way, it's basically saying that you just have to check that the acute triangles, that you get an acute triangle that's a representative of the particular elliptic curve, and you just compare those. You just compare those acute triangles to see if those are the same point in that moduli stack, and that tells you. Yeah. So what are we saying? We're saying that, like, I mean, there's all sorts of fun stuff related to this. I don't think it's just fun. I think it's actually useful and important in some ways, but I don't know exactly how to really argue that. But I mean, we're kind of saying that the moduli stack of moduli stack of acute triangles, appropriately construed, is an open dense. No, is it open dense? It's some sort of dense. I guess there's no, it's more than dense. It's like there's a surjective map from the moduli stack of elliptic curves to the moduli stack of acute triangles to the moduli stack of maybe the open dense set is the ones where,
truly acute
and yes, okay, truly acute, yes. Right. Yes, and we distinguish. Oh, damn it! What's that word I just looked up the other day? Chiral. Yeah, we include the chirality of the acute triangle, I think. So that's the right. We want the two halves of this. What do they call this strip? They call it some sort of strip. This is different from the Möbius strip, right? But maybe they don't call this. I don't know.
I don't know what it. Yeah, I'm getting. Okay.
Yeah. You're getting annoyed?
I'm getting confused. I'm forgetting, like, the normal moduli space of elliptic curves. It's the whole big fat strip there with some identifications on the
yes
on the boundary. Yeah.
Yes,
But
yes.
I'm remembering it as I say it. Yep.
I think that's right. I think that's right. So yeah, we're right. I guess we're right. Okay, I like the way you just sort of hinted at that. We're kind of saying that the two moduli stacks, acute triangles on one hand, elliptic curves on the other hand, they're basically the same except for glitches at the boundary. How do you treat, what kind of boundary conditions do you impose? So you impose some very nice periodic or boundary conditions when you're inventing the moduli stack of elliptic curves. But when you're inventing the moduli stack of acute triangles, you treat the boundary conditions in a much different way. They're just kind of walls or something like that.
Huh? Okay. Yeah, that's cool.
Yeah, I was just trying to, this barycentric subdivision that I drew over on this little flat picture of the triangle. I was just trying to remember where that goes. It's something like there or something like that. That's horrible picture. Right. Okay. Yeah. And that actually, right. So those are also like just like the midline. I should draw the midline in red too, or something like that. So those are also isosceles triangles. Am I saying that right? Yeah. So
Yeah.
I've been being really sloppy, but I know you can figure it out. Right. I mean, you can be isosceles at the distant corner, or you can be isosceles at this corner, which would be
right.
Yeah.
Yeah.
So you have to, as usual, you have to fix all the mistakes and everything I said, but when in the end, it worked. If you say it right.
Yeah, okay. Part of why I think it's hard for me to believe it is because it's drawn so badly. So
Yes.
Those red guys, to draw them right, they should only go up a height that's equal to the width of that strip. Whereas you drew them so that they go like much higher.
Right. So
but they should just go up to there, and that, yeah, something like that. And then
right. Those are exact quarter circles. Right. Yeah. Those are exact quarter circles.
So those are isosceles right triangles too, right at the top.
Yeah. Right. So you can see where the isosceles right triangles are.
Yeah, that's what I meant. Those dots there.
Isosceles. Where's the other isosceles right triangle?
Right there. Yes.
and that's over here in this flattened out picture.
Yeah, that's cool. It's weird. It's weird how stupid I was, because I would like using. I've sometimes given like an intro to stacks where I talk about the moduli stack of triangles in the plane, and I never connected it. I didn't draw it this way, so I never connected it to a stack of elliptic curves. But I could do it. You could do it like a better. Well, it would be more. It wasn't really what I was wanting to do, but it'd be fun. You could like first explain the moduli stack of triangles.
Absolutely, I think it's a great, intro type thing. So I mentioned this to Todd one time, and he said, "Oh yeah, so and so does that or did that." And I'm trying to remember who so and so was. Some big algebraic geometry person. I forget who it was. Yeah.
Yeah, no, I just never thought about it this way, so it's nice.
Maybe he said,
what
could it be Mumford? Did he say Mumford? I can't remember what Todd said. Ask Todd. But yeah, what did he say?
What are the non-acute triangles? Do they play any role in this elliptic curve game, or like some weird generalization of elliptic curves?
No. The non-acute triangles are just these, these. Right? I mean, any parallelogram gives you an elliptic curve. So these are just, those are, we're just singling out a very convenient way of normalizing the choice of the parallelogram fundamental domain. But it's more intuitive if you cut the parallelograms in half, think of them as acute triangles.
So the non-acute triangles correspond to points in other fundamental domains.
Yeah, yeah. I mean, they're over in this other,
Yeah. Uh-huh.
something like that. Yeah, yeah.
Yeah.
Right. They're just, those very skinny parallelograms that are really,
Uh-huh.
well, let's see that. I was trying to draw something not acute. I'm hoping that that's in an obtuse angle right there.
Yep.
I had the feeling that if I just do something very extreme, it would be out of here. But this does include the ridiculous things like you go up all the way there. Sorry.
Yeah. Right. Yep. So every non-acute triangle then has an acutization.
That's right. That's right. I mean, yeah, right. You get into a Buridan situation when it gets to be a right triangle, because like a square parallel or a rectangular parallelogram, because then you, as you mentioned, you have that choice versus that choice. Those are both ways of splitting it up into acute triangles. But I think that's the only time, or maybe I think that's the only time you have a choice as to which the because you'll sort of look at it, right? That's the only boundary type thing, unless I'm screwing up or something like that.
What about the circular part of the boundary down and below? Those are
also right triangles, right? That's the famous Euclid thing.
Yeah. Okay. Yeah. Okay. Yep. Okay. So can you go back to the picture of the
yes
original dispute?
Yes. So how do I do this? Don't tell me. Let's see. It's right there.
Yeah, there was a. Yeah. So there's this thing you can do to either of those parallelograms to turn it into the other, which was what was fooling me, I guess. So for example,
I think you're right. I think there's something going on here, but I can't put into words what it is. But go ahead.
I mean, there's a thing you can do, but I don't know what its significance is. So
yeah, same with me. Go ahead.
Okay. So anyway, maybe I don't need to say this.
Well, no, because it might. I came up with several things you could do, and I'm not sure what their significance is. But go ahead. Yeah.
So, I mean, this would be where it would be good for if I could draw on that picture. But anyway,
right.
So but anyway, look at the left-hand parallelogram. So you can chop it in half with a horizontal line segment. Yep, that one.
Right yes.
And then the top half, you can dissect into two right triangles, right? There's like a unique obvious way to take the top half of that. Yep, chop it right there.
But like this?
Yeah, no, well, yeah, I was thinking like you take the top half and you chop it into two right triangles.
Yeah.
And then you can move those two right triangles around and stick them onto the bottom half. Right, so there are two triangles above that line you just emphasized. And you could just rip those right triangles out and you could stick them into the bottom half of the picture in a way to turn it into a rectangle. I mean, you can always do this with any, you can always do this game.
But this is the dissection you're talking about, right? Like
yeah. But you get what I'm saying? You can take those top two right triangles.
Yeah, I did. Right. After you suggested this, I thought about something like it. And
so what I'm wondering, so anyway, my point is that when you do that, you get a rotated version of the right-hand picture.
Yeah.
So what I'm wondering about is like, is there anything important about that? Or
I suspect there sort of is, and it has something to do with Hecke operators.
I mean, you can always do that to any parallelogram, and you can chop it up like this and turn it into a rectangle of the same area. But here we're doing it somehow like in a way that's meshes very nicely with these grid points.
Yeah, it doesn't. It doesn't mesh that nicely with the grid points because there's this funny, earthquake fault here.
Yeah, I just meant that the dissection lines.
Yes, yes,
go along
yes.
grid lines.
Like I say, I have a feeling there's something going on with Hecke operators, which has to do with these sort of jumps from one lattice to another. I mean, but we're already dealing with jumps from one lattice to another. So I'm not sure how to express anything nicer than that. Right? We have the small square lattice, and we have this larger parallelogram lattice. Right. So the square lattice, that's a Gaussian lattice. And then this period lattice inside of it is a sub-Gaussian lattice. And that sub-Gaussian lattice, that's sort of like a Hecke jump. And well, we may, I know I'm not making that, I know that what I'm saying doesn't sound like it makes that much sense yet, but it may actually, and we might actually even talk about it today, depending on how much time we have.
Okay, so I'm willing to stop with that. I mean, that might even turn out to be like just another way of, just another spin-off of the fact that you're claiming that these two designs are in the same Galois orbit or something like that.
Right. I mean, there's all sorts of possibilities, but I'm not sure I have anything intelligent to say about it yet. So I think I'm just going to erase this part if I can.
Okay. So yeah. So anyway, so go ahead. Whatever other stuff you want to say.
Okay. I hope that's the right way. And now I go back to the other page. How do I do that? Bring back to the last page. Okay, this is today's page. Okay, so the next item on the alleged agenda is I want to say something about some vague ulterior motives that I have in stuff I've been talking about. So yeah, I hope that word vague, that was enough to give me, right, that was enough to
give you license.
Yes, license, exactly. I need a lot of license here, a lot of leeway to make all such silly mistakes. I think there's probably an idea here. There's probably many ideas here, but I'm just not sure I'm getting really close to them. But there's an idea I'm trying to approach here, or there's at least one idea that I'm trying to approach here. And so it's based on a bit of personal interaction between you and me, which is that you and I have been trying to explain to each other at various points certain ways of thinking about the Gaussian elliptic curve in particular. In both cases, we're probably doing it to try to learn and or teach things about much more general elliptic curves and things much more general than elliptic curves. I actually meant to go back to our little video list, the page where all our videos are listed, where I could find, so I wanted to find exactly what day it was that you talked about this. You may have talked about it on more than one day. I should when I locate that where that is, I should send you an email to know where it is. But so you were talking about a very motive oriented, right? This was in the process of really trying to learn about motives, learn and or teach about motives. And you were using the Gaussian elliptic curve as an example to try to like dissect it into motives.
Yep.
And really teach me about what that's all about.
Yep. Believe it or not, I don't think I noticed that it was the Gaussian elliptic curve. I just grabbed a polynomial that
you may actually have done more than one example.
Okay, well, there's one example that I gave a talk about where I was like counting points. I've thought about other examples.
Well, see, now I'm not 100% sure that you actually did the Gaussian example. If you had done the Gaussian example, then the thing that you might have noticed that makes it Gaussian is that, you know, so if I'm not saying anything too horribly stupid, so you can kind of dissect it in some sense into a single two-dimensional motive. No, did I say that right? What am I trying to say?
Yeah, a single two-dimensional motive.
Right. Okay. Yeah.
Not
Right.
real.
Right. The dimension of the motives is a real dimension. Right. So two real dimensional motive, two one-dimensional real motives, and a zero-dimensional motive. And the particular thing that happens for the Gaussian elliptic curve is that those two one-dimensional motives should basically be the same, I think, you know, because it's sort of kind of a square instead of just a parallelogram or something like that. So
I'll have to think about that.
now I honestly don't remember whether your two one-dimensional motives looked exactly the same or not. But I got if what I'm saying was correct, then it should be true that you were actually repeating the same one-dimensional motive. But maybe I screwed up. Maybe you didn't repeat the same one-dimensional motive. But I got the impression somehow that you were doing the Gaussian elliptic curve, but it could have been it could be because I just wasn't paying sufficiently close attention. Are you trying to check it out right now?
Would you recognize the formula? So let me just show you the formula for it.
I might. Well, again, the formula isn't unique, so I might recognize it on a good day.
The formula is what?
Isn't unique.
Right. And yeah. So yeah, I understand that. So, but this is a pretty simple version, so you might recognize this or not. Here's the one I was looking at.
That doesn't really look like it to me.
Yeah. Yeah.
So maybe I'm wrong. Maybe I'm wrong. Maybe you weren't doing the is that real? You were honestly looking for Lincoln diagrams, not for Dinkin diagrams?
What do you see that? Where do you see that?
In the search box.
Oh,
right where you're.
That's bizarre. Yeah. Okay. Yeah. That was just a typo.
Okay.
What's funny, what's really weird is that I just gave a talk about Dinkin diagrams, and Zoom automatically makes a transcript, and it transcribed it as Lincoln diagrams, like President Lincoln. But I was definitely pronouncing it right, but I see here that I spelled it wrong. So
do you think that explains me?
Unless Zoom is like spying on my Google searches, which I don't think is the case.
Okay.
Okay.
So
yeah. Okay. Anyway, this is it.
Yeah. This might easily. I don't know why I got the impression that you were doing the Gaussian thing. Maybe I just made some stupid mistake.
This one is very easy to count the solutions of in their case, but okay.
Okay.
Anyway, sorry, you have to reshare your screen if you want me to.
Okay. Okay.
So anyway, but yeah, I should definitely think about the Gaussian one from this motive.
Okay, then for purposes of my attempted thought, let's pretend that you did do the Gaussian one. So you can imagine, right? You can imagine trying to analyze the Gaussian elliptic curve motivically. On the other hand, I've been trying to, tell you about the Kronecker's Jugendtraum and using Gaussian elliptic curve as an example. And there's a real big overlap in what these two big mathematical ideas are telling you about the Gaussian elliptic curve in particular, for example. They're both telling you a lot about the points over the finite fields, and so it should be really interesting to try to understand in a good way the relationship between the information about the relationship between the information you get by thinking motivically about the Gaussian elliptic curve and the information that you get by thinking about Kronecker's Jugendtraum and how it applies to the Gaussian elliptic curve. I mean, that's just the simple-minded idea. Those are, there's just got to be all sorts of interplay between those, between the application of those two ideas to the to the Gaussian elliptic curve. And for someone who really understands this stuff, it may be completely obvious how they interact with each other. But for me, they both seem like mysterious, powerful machines, and I don't really understand yet how they relate to each other. The Kronecker's Jugendtraum is a mysterious, powerful machine, and the whole idea of motives as a mysterious, powerful machine. I'd really like to understand better how these relate to each other. And when I talk about Kronecker's Jugendtraum, I always link that with the art and reciprocity theorem, which really interacts with the Kronecker's Jugendtraum in a certain way. So, so my silly idea here is that one of my silly ideas here is to try to think about what maybe Grothendieck might have been thinking about when Grothendieck decided to fool around with these designs, these children's designs. Well, I mean, and again, this may be something that, somebody who really knows what they're talking about may know that this is obviously what's going on, but the designs kind of remind me of motive ideas. And in particular, in the case of the Gaussian elliptic curve, these Gaussian designs that we've defined and we've been fooling around with and thinking about how the Grothendieck-Teichmuller action acts on the Gaussian designs. These are coverings of the Gaussian elliptic curve, roughly speaking, or at least a lot of them are coverings of the Gaussian elliptic curve. And that's kind of what we're fooling around with here, coverings of the Gaussian elliptic curve. And so did I make the idea clear yet? It's this is a silly idea for an attempted thing to try to understand. What's the relationship? So there's Kronecker's Jugendtraum, and then there's this particular way we're trying to understand the Jugendtraum by sort of interpreting in terms of the designs. Like there are these Gaussian designs, which are based on the Voronoi tiling for the Gaussian integers. And so when you draw one of those Gaussian designs, you're drawing, the little edges and vertexes of different colors and things that you're drawing. Those are sort of right. It's sort of like we're taking a very nice motivic dissection, in some sense, of the Gaussian elliptic curve, and we're pulling that back, and it's giving us some sort of dissection picture of the covering of the Gaussian elliptic curve. And so yeah. So okay, let's try to make it a little bit more specific, a little bit more explicit. So this motive stuff gives you what? Like, is factorization the right word to use? It gives you like a factorization or something of the zeta function, or perhaps some L function, the zeta function of the elliptic curve.
Yep. Yeah, I like to just say it like lets you write the number of points on the elliptic curve as a sum of terms. That's sort of a logarithm of what you said.
Okay, okay. And so the application, this idea of understanding Kronecker's Jugendtraum in the context of the Gaussian elliptic curve, and moreover in the context of the Gaussian designs. So using the theory of designs to understand Kronecker's Jugendtraum as it applies to the Gaussian elliptic curve. That is something, one of the things you can do is you can take all that stuff and you can, and we'll probably try to do this, we'll try to understand what it's telling us about finite fields and, about points of the Gaussian curve over finite fields and how to count them and everything like that. And so the question is, if we analyze that using the theory of Gaussian designs, and if we compare that to this other thing that you have been telling me about analyzing the points over the finite fields of the Gaussian curve in terms of these motives, then can we somehow find a naive or less naive, nice direct correspondence somehow? Can we find some clear combinatorial thing that will link the combinatorics of these Gaussian designs to the motivic combinatorics that you were talking about? So that's sort of my naive, vague idea here. This is an ulterior motive, but again, an excuse for why I really want to fool around with these Gaussian designs. And like I say, it involves imputing to Grothendieck, all sorts of possible secret ulterior motives as well.
Yep.
So, and obviously I could be completely wrong about that, as well as being completely wrong about all sorts of other things. But that's the idea here. Okay. So, I'm now, that was just, like I say, that was just that was just propaganda for trying to give some ulterior motives as propaganda for why it's supposed to be, why it might be interesting, potentially interesting to try to learn about and understand some of the things we've been talking about. But right, I mean, there's specific ideas for projects in there, right? We really want to go back and talk about all the stuff that you've been talking about the motives.
Yeah.
We really want to see how it compares to this stuff that we're trying to understand here. See if we can get things to fit together in interesting ways.
Yeah. So one thing that's just like
Yeah.
another way to a different angle on what you said is like,
yes,
you could try to take an elliptic curve that we could do one that like nicely covers another elliptic curve. What do you call that? An isogeny? Well,
or something. Yeah, I don't remember the exact terminology, but yeah.
Just a cover. And then,
yeah.
So that will give a map between their motives. Functorially, it should. And then,
yes.
Then since motives are very much like a linear algebra type of category, some kind of Tanakian category or something like that. So then you should be able to like take that map and like really think of it the way you think of like a map between, say, group representations or something. So like with those, like,
yes,
what a map is if you know what it does to each irreducible piece. And those irreducible pieces are like the pieces that you were just talking about. Like there's a two-dimensional piece and two one-dimensional pieces and a zero-dimensional piece. And so when you're like wrapping one elliptic curve around another,
yeah,
that you get a map between a sum of 4 pieces to some other sum of 4 pieces. And I guess the wrapping must just be doing something like multiplying by different numbers on those irreducible pieces. It's like Schur's lemma should hold, that a map between irreducible motives is just like a multiplication by a number. So I imagine that those numbers must just somehow be conveying information about how the wrapping is like wrapping each piece of the one elliptic curve around the corresponding piece of the other elliptic curve. Like the two-dimensional piece gets like wrapped n times around the two-dimensional piece.
Yeah. Yeah. And this is definitely interesting. There's also things that are confusing me here. So, I mean, there are these unbranched covers and there are branched covers, and mostly we're talking about unbranched covers.
For right now, I was just like imagining an unbranched cover just to.
Right. But I'm just trying to figure out how this. I was wondering a little bit about how, can you see the unbranchedness in the. To what extent can you see the unbranchedness?
In the
maybe you can't see it. I don't know, but under different circumstances. In at the level of the motors or something like that. But okay, yeah.
Yeah, it's funny. It's funny because a curve, you can dissect it geometrically in lots of different ways.
Right.
Whereas for the motives, I don't think you can't really. Maybe you can, but every motive would have this like unique way of decomposing it into irreducible pieces.
Yeah. I was thinking about that too. Yeah. Right. And right. One warning I wanted to mention was that, a lot of things I'm doing with the Gaussian elliptic curve are very, very special to the case of the Gaussian elliptic curve. You could try to do analogous things for the Eisensteinian elliptic curve, but even in that case, it's pretty different because, when you, right, the motivic nature of the Eisenstein elliptic curve is not as right. The Eisenstein elliptic curve wants to have 3 one-dimensional things, but there's only 2 motives, so it doesn't fit with the motive. There's all sorts of things here that don't really make sense. It don't make sense yet, certainly. That was all supposed to be subsumed under my warning at the beginning that this was.
Sorry, what about the Eisensteinian one? That's supposed to have 3 something or others. What is it?
Yeah, if I guess what I'm saying is that if you at a very naive level, the Voronoi cells of the Gaussian elliptic curve. No, the Voronoi cells of the Gaussian integers are a kind of big visual reminder of the motivic nature of the Gaussian elliptic curve. Whereas if you draw the Voronoi cells of the Eisenstein integers, then at a very naive level, it's not as obvious how to naively connect that to the motivic nature of the Eisenstein elliptic curve. I'm saying something very silly there. It's just based on the idea that the Gaussian elliptic curve has to do with 2, and the Eisenstein elliptic curve has to do with 3.
Yeah.
So okay. So I'm proceeding here now, or I'm trying to proceed to doing actual stuff here now, instead of just giving propaganda. And well, right. So the big project here, right? A moment ago I was giving propaganda about big pictures that I don't understand. Now I'm trying to talk about much smaller pictures, this project that I'm working on to understand Gaussian designs as a special case of Grothendieck's general designs. And, the idea behind the project is that Gaussian designs seem to be conjecturally completely governed by Kronecker's Jugendtraum, which is a thing that's really easy to understand from it's been around for a while, and it's easy enough that it was discovered a while ago. I'm trying to emphasize that Kronecker's Jugendtraum is comparatively a really easy thing to understand. It's something that we can really easily understand if we look at it in the right way. And that might serve as a tool to, a bridge towards things that are, for me so far at least, more difficult to understand. It's supposed to be a bridge from things that are relatively easy to understand to things that might be more difficult to understand. More serious stuff about Grothendieck's designs and maybe motives and maybe the Langlands program, all sorts of serious Galois theoretic ideas that are more developed, more ambitious than the 19th century work of Kronecker's Jugendtraum. Yeah, so right. So one of the things I'm really trying to emphasize here is that, these Gaussian designs, they are so much easier than the others, right? So we shouldn't think that we're like understanding all of the, we shouldn't think that we're right away understanding all of the designs and all the whole theory of design just by studying the Gaussian designs, because they are so special among the designs. But still, that's good because we can really understand them. They're so much easier to understand.
Okay, yeah.
And then we can, dream about possibly using that understanding to climb the ladder of higher understanding of more difficult things. So, now I have to figure out what I actually want to do here. So, let's try to do some more examples of how I think the Grothendieck-Teichmuller action plays out in the case of these Gaussian designs. So, we already did that one example. Let me try to give you a bunch of other examples here. But boy, I would really, really like to prove that this actually works, right? Because this is all sort of conjectural so far, that these are Grothendieck-Teichmuller orbits. It really seems like it should be correct, but I really want to prove that it's correct by actually working out the Bellier data and comparing them and seeing that you're really getting things in the same Grothendieck-Teichmuller orbit. So let me sort of try to remind us of how we got the example that we've used already. So what did I do? Let me think. So, well, we were somehow focusing on the prime p equals 3. And we were thinking of Gaussian designs. I guess we're thinking of, right, okay, so, I've got graph paper on my screen here, right? And the vertexes, we can think of that as the Gaussian integers, roughly speaking. And now we're interested in sublattices of that lattice of Gaussian integers. And we want sublattices of index 3. And this, right, so I guess that has like, I don't know, what's a good, how many of them are? Is there a whole bunch of them? Is an infinite number of them? But I think maybe in the way that they orient themselves to the Gaussian lattice, maybe there's just Am I being silly here? So like, I mean, what am I trying to say? That you could have, you could take 3 as one generator
Yeah.
of a sublattice. And for the other generator, you could take, don't tell me, you could take, let's see, I'm beginning to try to draw little pictures here to remind myself of what this looks like. So 3.
I'm resisting saying anything.
Yeah, you should resist. Just I'll figure it out. I'm trying to think of, what are the, I'm trying to think of like numbers up there or something like that. So, because that'll give me a nice selection of
Yeah.
possible lattices of index 3. So those are numbers that are like, right, the real component might be, let's call it J or something, but the imaginary component would be I or something like that. And if we're thinking mod 3, then that really just gives us 3 possibilities. But there's a 4th possibility that we should include. I guess what I'm trying to do, right, what I'm secretly trying to do here is I'm trying to get all of the points of the projective line over Z mod 3 included in the game. And so far we only have 3 points of the line. So how do we get the 4th one? The 4th one, okay, do you want to tell me? I mean,
now that I
what?
Now that I don't know the answer, you don't want me to.
Well, so I mean, we're trying to get all the slopes here. So we have, slope.
Oh, 0? I mean, what are you trying to, I don't know why you want to, what is this other thing? This is.
Yeah, I mean, I guess so far we have infinite slope and slope. Right, I guess I've got the reciprocal slope, so maybe I should have done it the other way around or something. So, but right, we didn't include slope 0 yet. So what am I trying to say?
I don't know. Why do you want to conclude that? I mean, that's not going to be an elliptic curve, right? It's going to be like some kind of infinitely squashed elliptic curve or something.
Well, I'm not sure. I may not have said it carefully enough yet. I'm just trying to get, what am I trying to say? So from a sub-Gaussian lattice of index 3, you get a point of the projective line. Yeah, let me try to draw the Gaussian integers modulo 3. So it's like inside that box. The vertex is inside that box. Okay. Right. And then there are these. No, it's not. I did that completely wrong. What did I do? Oh, it's the boxes inside that box. But maybe I should have made it the vertexes inside that box. I have to quickly decide which it should do. Let's see. So I'll do it the other way around. I'll do it we'll think in the terms of the vertexes. So it's like that. Okay, so there's the origin, 0, 0, or 0, and there's 1, and there's I, there's 1 plus, no, sorry, I is up here, sorry. I forget that people do it that way. I and 1 plus I, yeah, it's just the Gaussian integers, but it's mod 3. So I picked as these representatives instead of, I picked the representatives where it's 0, 1, and -1.
Okay.
And so the points of the projective line are these 4 points. Right, and each of those 4 points gives us a lattice, a sub-Gaussian lattice of index 3. Right, by just making it let me give an example here. So there's this one. So it's got that and that, so it would be like this and this and this and this. And then it would be 1, 2, 7 here and here. So am I doing this right? This is a lattice of index 3.
I guess so, yep.
And yeah, so how many other lattices of index 3 are there? Is there an infinite number of them? Or is there just these 4 of them? Maybe it's just these 4 of them.
Does this have to do with like
Right. I mean, you can write down any 2 by 2 matrix of determinant 3, but that would giving us like different bases for these same sublattices. What were you saying? That's what you were saying.
Yeah, never mind. So how many are you getting? Assuming that
4. Corresponding to the right. These are the points of the projective line over Z mod 3. Sorry. Damn, how do I fix that? Sorry. Yeah, what am I trying to say? So right, any lattice of index 3, when you sort of regularize it, it's going to give you, a square lattice of index 9, or at most 9, or something like that. But then what am I trying to say? You're just like dealing with the Gaussian integers modulo 3, but just thought of it as an abelian group. And you're sort of, right, you're modding out by that idea. Well, okay, you're taking the Gaussian integers modulo 3, which is that 9-element, I guess it's a 9-element field, but we're just thinking of it as an additive abelian group for the moment. And we're looking at its additive subgroups. And there's just 4 of them, because it's, it's a 2-dimensional vector space over Z mod 3. And the projective line over Z mod 3 has 4 points. And right, I mean, that picture is suggestive, right? A point of the projective line is just a line through the origin. So that's, that's this, those are these 4 points, these 4 lines through the origin in this little mod 3 world.
okay.
So
what does the 4th one look like? So you drew, for some reason, you get 3 of them by your first description.
yes.
Which is the description I understood. And
Right,
then
right. So let me see what they are.
Generators
So,
for the 4th one.
right. So let's see. We have, which 3 of these are the ones that we're getting from that? So we have.
I think the 3 ones that look like non-horizontal lines in your little.
Is that right?
Sure, because that looks like those dots up there are like.
Okay, so how to get the horizontal line? So the horizontal line is generated by 1 and 3i or something like that.
Oh, is that what it is? Okay.
And again, that should be.
Oh, I see. Ah, sneaky. So that's, yeah, I see. So that thing is.
Yeah, I mean, right, the extra point on the extra point on the projective line is the line of infinite slope. That's one way to think of it. And it's sort of like that, except somehow I got infinite slope and zero slope backwards in this setup, but that's okay.
Yeah. Sure.
So yeah, so each one of these Gaussian sublattices of index 3 can be taken as the period lattice of a Gaussian design. And we can try to understand the Grothendieck-Teichmuller action, Grothendieck-Teichmuller action, how do you pronounce it, on those Gaussian designs. So we have 4 of them, you know, and we want to know what the orbits are here. And we're figuring this out by using my intuition about what Kronecker's Jugendtraum is telling us. So you know, we're just getting the Gaussian integers that are relatively prime to 3 to act on these lattices by just, you know, they act sort of by multiplication, but, you know, because we're working mod 3 and everything, it will actually, you know, it will actually stay inside this set of 4 lattices. And
okay, can you do it? Have you done it?
yes. So okay. So let's think about what we're saying here. We're saying that we've got this 9-element field because 3 does not split over the Gaussian integers, right? Because it's not 4n plus 1, it's 4n plus 3. So 3 is the kind of prime that doesn't split over the Gaussian integers. So we're actually getting a 9-element field, not like a product of fields or anything like that. So we've got a 9-element field. So GL1 of the Gaussian integers modulo 3, that I guess that's my notation for the Gaussian integers. Z subscript G. GL1 of this field is a, you know, cyclic group of order 8. So okay. Right. Okay. So cyclic group of order 8. So that means, you know, that makes it sound like we could potentially have 8-element orbits. But that's going to be a little bit hard to arrange since we've only got 4 things to act on. So what am I trying to say here? I mean, but there's also what am I trying to say? So I think we actually only have 2 things to act on. I mean, we have we have these 4 sublattices, but I think they're equivalent to each other in pairs. Now, what do I mean by equivalent to each other in pairs? I think I mean something like, what's their orientation to the Gaussian lattice? Yeah, so I think the 2 diagonal ones both have the same orientation to the Gaussian lattice, right? And the 2 horizontal ones have the same orientation to the Gaussian lattice. So, right, obviously I'm being very sloppy here and trying to say stuff and then afterwards analyze and figure out what I really mean. But that's what I think is going on here. I started out saying that we have 4 sub-Gaussian lattices here, and we do. However, they're actually grouped into just 2 orientations to the Gaussian lattice. So, you know, there's already some sort of grouping here before we even get into the grouping of the Grothendieck-Teichmüller orbit, right? The things that are related by the Grothendieck-Teichmüller action, those are more distant relatives than these really close relatives that I'm talking about right now. So, you know, that's slope 1 and slope -1.
So you're just letting, so yeah, when you're talking about orientations at this first stage, what group are you defining orientations with respect to?
I'm hoping it's obvious. I don't know. Let's see. Well, let me pretend to answer your question by pointing out.
Seems like if you're talking about like the group of units of the Gaussian integers or something, because you're rotating one picture 90 degrees and saying, oh.
I think you're right. I think you're right. Yes. Okay, good. That's very helpful. So that's one. That's yes. I think you're right. I think that's right.
So that's like GL1 ZG, not GL1 ZG mod 3. That's a smaller group, the group of units of the Gaussian.
That's right. That's right. That's right. That's right. That's right. So, okay. So one of the things you're saying here is that there's GL1. That's actually a subgroup. Now, in you know, I mean, it seems in some ways it seems like an accident that it's a subgroup, but it is a subgroup. You know, if we do more general examples, we may have to think about whether that homomorphism is injective or not. Depending on how general we get, it might always be injective. Yes, yes, right. So that action is right. Those are the really close relatives. You know, never mind being in the same Grothendieck-Teichmüller orbit. Those are in the same. Yeah, those are just the same. Those are more of the same lattice. The comment I was going to make was that if you look at like some modular curve, right? There's some modular curve. There's some very nice modular curve whose points really represent superimpositions of 2 kinds of lattices that are this distance apart. That one is, you know, index 3 sublattice of the other. Did I say that right? Maybe I shouldn't have said of index 3. Maybe I should just sort of said that, you know, these lattices that have. No, I think that's right. Yeah, something like that. Yeah, when we start thinking about modular curves, we'll really think of these as having to do with orientations of lattices to sublattices. So, I mean, there's an interpretation, right? The very not clearly thought out comment I'm trying to make here is that there's some interesting way to classify the things we're trying to classify here by looking at certain modular curve and seeing, oh, the Gaussian points on this elliptic curve are actually classifying the things we're trying to classify. It's the orientations of a Gaussian lattice to this other kind of lattice. And then we'll repeat that story when we work with the Eisenstein designs as well. But right now we're doing the Gaussian case. So yeah, okay. Being very sloppy here, but hopefully we'll actually make some progress here. So, okay, so you just pointed out a very important subgroup there. But there's another very important subgroup, which really is not just this more trivial action, but this Grothendieck-Teichmüller action is really something like, what do I want to say? No, I sort of said that backwards. Sorry, I sort of said that backwards. Am I saying this right? What am I trying to say? I'm not sure what I'm trying to say. So let me write down this subgroup first. I think the point is that I'm trying to write down all the subgroups I can think of that act trivially as far as the Grothendieck-Teichmuller action is concerned. And so we're going to take a co-kernel. We're going to mod out by these things, and to find the actual Grothendieck-Teichmuller group, we're going to sort of mod out by this stuff. So what am I trying to say? I want to say GL 1, Z mod 7. That's going to act trivially here.
So where does Z mod 7 come from?
So this is like the real scalars instead of the complex scalars, the real Gaussian scalars. And right, these can't change, right? How could these possibly change the shape of the lattice? These can't change the shape of the lattice. You're just multiplying by a real scalar. So you're getting, a lattice that's still sticking in the same, you're just magnifying it by a real thing. But, because we're modding out by 3, it's going to close up. Do you see what I'm saying? It's just.
I don't get where Z mod 7 is coming from. So that top group.
I'm sorry, did I say 7? I'm sorry, I was supposed to say Z mod 3. Just when I was talking to somebody else, I used 7 as an example instead of 3. I'm sorry.
Okay, that's a lot.
That's horrible.
A lot less mysterious.
that was a horrible.
Okay.
That's really horrible. Right. In any moment now, we're about to switch to the example of 7, and then an arbitrary prime P that's equal to 4n plus 3. That's that's congruent to 3 mod 4. So 7 is the next example after this, but right now we're doing 3.
Okay.
Yeah. So yeah, so what I'm saying is we want to mod out not only by the subgroup that you mentioned, but also by the subgroup that I mentioned. And so we actually want to mod out by the, the sort of combination of those 2 subgroups. And the combination of those 2 subgroups is this sort of cross-shaped subgroup.
I don't know what that means.
Yeah, it's sort of shaped like a cross. I mean, 1 bar of the cross is your subgroup, and 1 bar of the cross is no, 1 bar. Okay, I said that wrong. 1 bar of the cross is my subgroup. That's the GL1 Z mod 3. That's the real bar of the cross. And then your subgroup is just the 4 cardinal directions. North, south, east, and west, right? That's the units of the Gaussian integers, the cardinal directions. And you combine those 2.
Oh, I see. Sorry, I was. I don't know. Yeah. Anyway.
Yeah, and there's a non-trivial intersection of these 2 subgroups, right? There's like.
There is.
Yeah, because east and west are 1 and -1, but 1 and -1 are both real. They're both in Z mod 3. They're actually 1 and 2. 2 is -1 mod 3, or something like that. Or did I actually accidentally get into the situation where it's so degenerate that? No, I think even in this case, that right, 1 and -1 is half of, yeah. Okay.
Yeah.
Okay.
Yeah. Okay.
So right. So this was actually just warm up for the case, like I say, where we'll have 7. So it's like 1, 2, 3, 1, 2, 3. Doing that right? That doesn't look square, does it? Maybe it is a square. So this is like the Gaussian integers mod 7 now. And once again, we get this cross-shaped subgroup. Which is a mixture of the 2 subgroups Well, so back in the case, the prime p equals 3. We're kind of, I'm trying to convince us that we really do just get a 2-element orbit, and that it really is just the whole Grothendieck-Teichmüller action in that case of the prime 3 on all those lattices, all of the Gaussian designs that come from those lattices. It's just a 2-element orbit. The whole thing is just one single 2-element orbit. But now I'm switching to the case p equals 7.
Okay.
And I'm saying a lot of the things are similar. We still have this cross-shaped group that acts trivially, but all the other, but okay, so what are we saying? We're saying that, let me try to do a little bit of numerology here. So this was what? This was an 8-element group. This was a 4-element subgroup.
Yep.
This was a what? 2-element subgroup. And they intersect in a 2-element subgroup, which actually happens to be all of this thing over here. So, right, in this case, we're ending up with, it's what? P squared minus 1. That's the 8. And then it's divided by the product of these two, except there's a factor of 2 intervening there.
Yep.
So it's p squared minus 1 divided by 4 over 2 times p minus 1, I think. So this should simplify out to p plus 1 over 2, I think. So what I'm saying, yeah, let me start listing some primes in this congruence class. So we've got 3, let's see. So P is could be 3.
So that thing where you wrote, it looked like you're multiplying two big bracketed expressions and you meant it's divided, right?
What did I do? I may have screwed up. Are you saying I wrote it wrong?
You just wrote it wrong. Those two guys in parentheses are one's divided by the other, not multiplied.
Like that?
Yeah. Yeah. Okay. Yeah.
Okay. Thank you. So let's see. I'm just trying to list the first couple of primes in this congruence class. So it's 3, 7, 11, 19, 23. 31. And so p plus 1 over 2 is 2, 4, 6, 10, 12. I'm doing that right?
Yes.
10, 12, 16.
Yep.
Okay. So
So now you're
yeah, I'm
right.
right.
Equals 7 works the same way.
Say that again?
You're hoping that the thing you did for p equals 3
Yeah.
so works. So like that the overlap of the two groups is sort of the same.
That's right.
Hmm.
Yeah, that's right. That's right. Yeah, I think that I'm right. If I didn't screw up, then I think this formula should actually work. So that we should actually be getting, for the prime p equals 7, for these lattice sub-Gaussian lattices of the index 7, giving us Gaussian designs. I seem to be claiming that we're getting a Grothendieck-Teichmüller orbit, a cyclical Grothendieck-Teichmüller orbit of size 4. And I hope it's sort of clear how you get these Gaussian designs. So again, you just take this period, you take one of these lattices, sub-Gaussian lattices of index 7, and you use that as a period lattice for a Gaussian design. And if my if my conjecture is correct, if my understanding of Kronecker's Jugendtraum isn't just really off base, then so this is giving us some good examples of the Grothendieck-Teichmüller option. Like I say, this is so trivial compared to the general Grothendieck-Teichmüller action, but I think it's a really good way to try to get an idea of what's going on here. So I have fun doing really concrete calculations here. So I would like, for this example of p equals 7, I would like to, draw the actual 4 Gaussian designs, see, what do they look like? Et cetera, et cetera, et cetera, and understand all sorts of things that are going on here. So like, let me mention something that might be interesting, that might be going on here, okay?
Can
Do you
I
have a comment or question?
No,
Go
I
ahead.
have a dumb question. So why do you know they're all in the same
Well,
orbit?
I may have screwed up, but I was trying to figure, when we multiply, this is the most that I could think of that would act trivially. When we act by one of these other scalars in here, I think it's almost tautological that it's going to take us from one of these to the other. I mean, right, the whole group is a cyclic group. We've got a cyclic group acting. I think it's almost like acting on itself here, but it's acting on a quotient of itself. And I think it's just kind of acting on the cosets of this cross-shaped group. I'm being very sloppy here, but I think that's the way it's going to work out. What?
So so the point of this GL1 Z G mod 3 is by art and reciprocity or something that is the abelianized Galois group. Is that what you're saying? I don't even know if.
I think that's right. I think so. Well, you know what? It might even be. Yeah, I'm right. That's very good that you said that. It's something like that is going on, and we should try. Yeah, that's one of the things we really want to clarify. We want to clarify the statement that you just said to the point where either it's actually true or we actually understand it or something like that. But yes, the art and reciprocity theorem should, as one of its consequences, tell us something very directly, pretty directly, tell us something about the Galois group of a certain abelian extension of the Gaussian integers, which is basically generated by all the coefficients of all the 3 torsion points, or P, for general P here, the P torsion points on the Gaussian elliptic curve. That turns out to give, an abelian extension of the Gaussian integers or the Gaussian rationals. And, it's a mixture of Artin's reciprocity theorem and Kronecker's Jugendtraum says that, that particular extension, that particular abelian extension of the Gaussian rationals is, has this Galois group that we're talking about here. And when I say that one that we're talking about here, I think it's probably the cosets of this cross-shaped group. So I think we're actually modding out by both of these. Is that what you were suggesting? That we should mod out by both of them, or were you saying just mod out by one of them?
No, I was just trying to make sure I understood where the GL1 ZG mod P, what the hell that has to do with Galois. theory. So now let's see. So I was, so that's all I
Oh,
was.
I thought you were saying something about the co-kernel here, that the art and reciprocity theorem is telling us. I'm being
You're
really
reading more
sloppy
into
here.
my comment than I was trying to
Okay.
put in there, but maybe true though.
Okay. It sounds like you were trying to say something about art and what art and reciprocity theory tells us about abelian extensions of the integers. Whereas I was trying to think about what it tells us about abelian extensions of the Gaussian integers. And those are both relevant here.
No, I was thinking
Yeah.
about the Gaussian. I was thinking about the Gaussian.
Oh, you were thinking about the Gaussian.
And how that top group there.
Oh, yes.
Yeah.
Right. That top group is going to be, yes, something about a Galois group. But I think you do end up modding out by these two subgroups or something like that, or at least you mod out by one of them. But I don't want to worry about that too much yet, because that would mean we were actually understanding the art and reciprocity theorem. And the art and reciprocity theorem is sort of very fuzzy in my mind about the different formal ways of stating it. So you're definitely on the right track.
Okay, that's good enough. Yeah, that's good enough for me. Oh boy. Yeah.
No, we really are going to understand this stuff. This is really okay. So we're trying to wrap it up in 5 or 10 minutes here. So I'm mostly I'm just going to manage to give you semi promises about where we're going to go from here in the rest of the time that we have today. But yeah, so like one of the things we'll do here is we'll try to understand what's going on with the other congruence class, primes that are congruent to 1 mod 4, primes of the form 4n plus 1 instead of primes of the form 4n plus 3. And I started doing calculations with that. I didn't get very far yet. So that's for next time or something like that. It should be, same kind of work. I don't think it's going to be trivial. I think it's going to be interesting. But it's just a part of understanding Kronecker's Jugendtraum in the context of these Gaussian designs and all that stuff. So that's another calculation project. Just doing the other congruence class. Let's see. So another calculation project is doing the same thing that we're doing here for the Gaussian designs, but doing for the Eisenstein designs. So let's just try to fool around with that for a second, okay?
Okay.
So for the Eisenstein designs, we're going to have an asterisk-shaped subgroup instead of a cross-shaped subgroup.
Uh-huh.
And if you think about it, I think the easy, I hope I'm not screwing up here, the easy congruence class, the ones where the ones where you get, you mod out by an ordinary integer and you get a field, you mod out the Eisenstein integers by, I think that should be 6n plus 5. So that would be, what were we saying? That would be 5, 11, 17, 23, 29, 41, 47, 53, 59, etc. And that's supposed to be a 7 there. I don't know if you can read that. So 7.
Yeah.
So I think it's going to be like, GL, the Eisenstein integers. No, what am I doing? I'm saying it wrong. GL1, comma, the Eisenstein integers modulo P. So P is, this prime 6n plus 5. And then we're, modding out by this asterisk shaped subgroup. So it's like GL1, what is it? GL1 Eisenstein integers?
Yeah.
That's a 6-element cyclic group or something like that. And then
Yep.
this is just GL1 Z mod P or something like that. Did I do that right?
Well, you're doing it the same way.
Right. That's right. That's right. And, so like I say, we're modding out by this asterisk shaped subgroup. So what are we getting? We're still getting p squared minus 1, but we're dividing by
6.
p, what?
No. Yeah, go ahead.
Dividing by p minus 1
times 6. Then a cancel, and then a correction factor. They both
times 6 over 2.
Yeah. Because -1 is in both.
Okay, so this is going to be equal to what? P plus 1 over 3,
Yep.
which seems promising in terms of, 6n plus 5, that'll be divisible
Yep.
by 3. So, okay, so this is P, and this is P plus 1 over 3. So we're getting 2, am I doing this right? 2, 4, 6, 8, 10. I'm doing that right? And then
Yeah.
14, 16, 18, 20. Okay. Yeah, I still have a thing to say before I quit here. One of the coincidences that's going on here, presumably it's not a coincidence, but at this point it sort of seems like a coincidence, is that the Gaussian integers and the Eisenstein integers, they have all sorts of mystical significance. So, the Gaussian integers is the base for quartic reciprocity. And the Eisenstein integers is the base for cubic reciprocity. That may have been how Gauss and Eisenstein were thinking about these things. They were trying to invent quartic reciprocity and cubic reciprocity. And so there's all sorts of things to say about that, but right. So I'm only giving you a very minor preview here of that, and just kind of a numerological preview here. So one thing that's going on here is that, the Gaussian integers has a whole bunch of abelian extensions, and we're kind of getting a bit of a view of all of them here. We're kind of, in a way, we're sort of surveying all the abelian extensions, or at least we're getting hints of all the abelian extensions of the Gaussian integers. If we study this in more detail, we'll kind of get a sense of all the abelian extensions of the Gaussian integers, and what Artin reciprocity theorem tells us about that, and what Kronecker's Jugendtraum tells us about that. So we've got, there's all of these abelian extensions of the Gaussian integers, but not all of them are really that relevant to quartic reciprocity. It's only the quartic extensions of the Gaussian integers that are relevant to quartic reciprocity. So that means I'm, looking at my little table here, and I'm circling the ones here that are divisible by 4. Because I'm hoping that those designs, the ones where this is divisible by 4, so the Galois group, right? It looks like there's some quartic extension of the Gaussian integers that's acting non-trivially there. And, or this is some quartic extension of the Galois group. This, what? This is the Galois, there's this quartic Galois group that should be acting visibly on the designs in this case. So I'm hoping we can somehow modify these designs in these cases where this number is divisible by 4, so that we'll actually be able to get something that's, I mean, maybe we'll even get like, I don't know, like this one with 7 where it's 4. Maybe this one actually has to do with the 4th root of 7. That's just a wild guess. And maybe this one about 23, maybe that has to do with the 4th root of 23. I'm not quite sure. I'm not sure exactly how this game works. But I've seen patterns a little bit like that in similar cases or something like that. So, maybe we'll get a design in which the 4th root of 7, right? Maybe this particular design, or it's actually a group. It's right. It's a quadruplet of related designs, Gaussian designs, which have like area 7 or something like that, and we may be able to see, the number 4th root of 7 in that design, and we can, we can try to, we may be able to get really visual pictures, nice design pictures of quartic reciprocity and cubic reciprocity. So it's just one of the minor spin-offs here. And now I really am out of time.
Okay, so, yeah, sorry, I have to go.
Okay. So thanks a lot. I'll see you. Bye.
Okay, sure.